So my name is Mateus Oglieri. I'm a storage architecture intern for Western Digital, and today I'll be talking about my proposal titled RISC-V support for persistent memory systems. Okay, so as a quick summary of what persistent memory is, I like to think of it as a hybrid between storage and memory. We have the byte addressable load store interface of memory and the persistency property of storage, and combined into one. So persistent memory is a field that I've been working on during my PhD for a while, and it's supported in hardware through non-volatile memory devices, such as Intel's 3D Crosspoint, battery-backed DRAM, and VDIM phase change memory, etc. However, it's also supported in software, and there's a number of works, persistent memory aware file systems, etc., that utilize persistent memory. So let's talk about support for persistent memory. So persistent memory already has support from a number of instruction sets that shall not be named, but not RISC-V. And so this is what my talk is about. It's about what support does persistent memory need that we can do for RISC-V. So as a quick summary of what persistent memory relies on, there are a couple of fundamental techniques that is very critical for persistent memory to work on a system. One is, for example, uncacheable logging, the ability for the processor or the core to issue memory requests directly to memory, bypassing the cache hierarchy. There's also cache flushing. We want the processor, the CPU, to be able to issue requests to the cache to flush or force the write back of specific cache lines back to memory. And we also want the ability of this technique called a memory barrier, which when you insert a memory barrier into a code, all store instructions that occur prior to the memory barrier must complete and commit to memory before any store instructions issued after the memory barrier. So I'm here to propose the changes that would be needed in order to bring up RISC-V to be able to support persistent memory research. So some new instructions that I propose, they're fairly straightforward. I call these two UCST, which is uncacheable store, and UCLD, uncacheable load. They look similar to standard store and load instructions with their source registers and offsets. However, the difference here is that uncacheable store would write directly to memory, bypassing the cache hierarchy completely. And in fact, we can go further and say we can distinguish between the different kinds of stores to have an uncacheable store to allow for writes to memory of word-sized, byte-sized, and half-word size, such as shown here. So we could have a UCSW, a UCSB, or a UCSH. These are not references to any University of California schools, by the way. So UCLD, I'm from UCSC, so this is very confusing for me as well. So similar to a load instruction, UCLD would function similarly. We want to be able to read data from memory directly without having to go through the cache. And similarly, we can have a UCLW, UCLB, and a UCLH instructions for word, byte, and half-word loads, respectively. Other instructions that are important, an S-fence instruction, so this is what I mentioned before. An S-fence is a memory barrier for store instructions. So if you have an S-fence in your code, then any store instructions that occur before the S-fence must commit to memory before any store instructions occurring after the S-fence. Additionally, CLWB, which we provide a source register and an offset. CLWB stands for cache line writeback. So the idea for this instruction is that when a processor issues it, it directs the cache and forces it to write back a cache line containing the address specified by whatever is in the source register plus an offset. And this writeback will only occur if the cache line is dirty. So typically, when you have your cache that follows some sort of writeback scheme, rather than wait for standard eviction policies or for it to write back on its own, we want to be able to direct it and tell it, please write back. And this will only occur if the cache line is dirty. So if the programmer isn't sure or issued this instruction and the cache line has already been written back, then this instruction will do nothing. And additionally, the cache line that gets written back will not become invalidated. It will still remain valid in the cache for use by the program. So the specifics of how to implement these instructions may vary, but in general, the three different parts of the RISC-V system that we would look at to modify, the first being the processor. So in order to support new instructions, we need to add them to the instruction set and any logic for decoding along with it, specified by number 1 there. Number 2, the cache controller. So the cache, normally you receive a request from the processor. It's a read or write, but we want the cache controller to be able to recognize a new request. Could call it a cache write-back or a cache flush. Additionally, the memory controller. So if we want for our RISC-V system, our processor to be able to write directly to memory to bypass the cache hierarchy, then it needs some kind of memory controller or something in hardware somewhere to allow that to happen. Could be via write combining buffer or what have you, but this functionality would be necessary as well. So let's talk about why I think these changes are important and what's the impact of research and in academia. Software-based. So right now, there's most of the work in persistent memory is software-based. So it relies a lot on the programmer or some API implementing persistent memory, and that requires all those instructions I mentioned to work with. Now, right now, we use other more commodity instruction sets for our work, but we want to be able to bring up RISC-V to be able to do this work as well. So doing these changes will allow software-based persistent memory research to utilize RISC-V. Additionally, some works actually do more hardware-oriented approaches to persistent memory and hardware-based implementations. And although those works may or may not use those instructions, just being able to implement the instructions in the RISC-V architecture means that the data paths will now be available for researchers, engineers to work with, such that any hardware-based solutions can rely on the data paths present in the microarchitecture to implement persistent memory and whatever their design is. So even if the instructions are not used, the basic functionality in order to enable persistent memory will be there with these changes. So let's talk about more specific applications. So the first thing I like to bring up is Whisper, published in 2017. It's a benchmark suite comprised of 10 persistent memory applications. So most persistent memory work and research that's done for evaluation, similar to how we have SPEC and other benchmark suites, persistent memory research likes to rely on this benchmark Whisper in order to evaluate their designs and show the results that can be compared across systems. Currently, Whisper cannot be run on RISC-V. I've tried, and unfortunately, it cannot even compile. And one of the reasons for this is that the Whisper relies on some libraries such as pmemlib and pmem.io support, libraries that are written in assembly, not fit for RISC-V. So implementing these changes in RISC-V would allow the experiments to even be run on RISC-V, which I think is very important. Specifically, let's talk about some persistent memory-aware systems. More on the software side, Nova is a persistent memory-aware file system. You may have seen a PMFS, published in 2016. Basically, it relies on these instructions that I outlined to be able to implement their file system. And additionally, crash consistency and recovery is very critical to guarantee consistency when you're dealing with persistent memory, as outlined in the paper by Peli in 2014. So without these changes to RISC-V, none of this would work and persistent memory would be possible. Shifting over to the hardware side. Even some hardware-based persistent memory designs, which are newer and more recent than some of the previous software ones, would benefit greatly from these changes. So I'll reference my own paper, Hardware Undo Redo Logging, that I published earlier this year, as well as some previous papers, Atom and Do TM, both in 2017, which have more hardware-focused approaches for persistent memory. And that just having the instructions or even the data path architecture to support persistent memory functionality would benefit greatly as well. So I would say that these changes would open up RISC-V to lots of persistent memory research, but also allow us to have a better complexity analysis for our underlying systems when implementing persistent memory. So it would allow for direct study of metrics like hardware metrics like area, cycle time, energy. It would also allow us to take our persistent memory systems, say that as extensions of a RISC-V system, and program them onto an FPGA. And it'll give us more agency and ability to have RTL designs based for persistent memory. So I'm going to shift gears a little bit and talk about how these changes would be relevant to my work now at Western Digital. So at Western Digital, I have this background, this framework for a design for my previous paper on a hardware-based persistent memory solution that is very efficient, more so than some of the other software approaches. So I want to take this hardware block, which in my paper I've had to implement using a high-level C++ simulator, using unnamed instruction set, and I want to be able to take this design and apply it to RISC-V. I want to see how it'll work on a RISC-V machine. So I have the boom, the rocket chip implementation, the RTL and chisel. I want to take my design, I want to implement it in RTL, connect it to the rocket chip, the boom chip, and I want to finally take all those and run it on an FPGA. So this is something that these changes will enable, and also any additional challenges that I wasn't optimizations that I can make that I haven't been able to detect before due to using a high-level simulation, I'll be able to see now. So this is the Xilinx FPGA board that I use for my work. So these changes would be very useful. So not only would it bring RISC-V up to the level of other instruction sets, but because of the open source nature of RISC-V, it will allow us to take work further than what's been possible before. So yeah, that's why it's important to me and why I think that this would be a very good way to bring up RISC-V and make it big in the persistent memory community. So thank you very much, and I'll take questions, I guess. Yes?
Explain to me in simple English why non-volatile main memory causes these things to be needed instructions when theoretically, if done correctly, it's transparent to the programmer whether the memory is volatile or non-volatile.
Right. So the reason that persistent memory needs these techniques is because persistent memory isn't just non-volatile memory. So you can have your main memory be completely non-volatile. You're running your program, and suddenly there's a power outage or a crash in the middle. But once you reboot your system, your data may be corrupt. It may be in a state that's neither the old stable state that you had it before or after the changes you made. So persistent memory with techniques such as logging, shadow copying, et cetera, allows it so that if any errors occur anywhere, the data will always be in a stable state. Either it will be the data you had before any changes were made or the data after the changes were made. So that's why it's important to support this.
Hi.
You can tell this got us a little bit excited. So are you saying that persistent memory should not be treated as cacheable memory in the system?
So specifically, okay, so persistent memory can be cacheable. However, that some of the techniques used for implementing persistent memory, such as logging, so the premise behind logging is that any changes you want to make to your non-volatile device or persistent memory, you log the change first, and then you write it out and commit to memory. Now, this log is handled like any other memory request. It will go through the cache. However, this log will only be used in the case where you have a crash and you need to recover your data. So if you cache this log, then you have a bunch of data in the log that possibly evicted useful data that may never be reused, especially since typically for the persistent memory work, caches are volatile. So if there's a crash, whatever log was in the cache will be gone anyway. So it doesn't make much sense to cache the log when doing persistent memory. So a lot of persistent memory work relies on being able to bypass the cache hierarchy for writing the log.
I've been saying this too much lately. Probably before you were born. I know. I actually built systems where it was very common when caches were viewed as evil. In the page table entry, there was a bit that says uncacheable. So when I translated from virtual to physical, I said, this goes to and from no instructions, and if you wanted logging or anything else, that was just a side effect of uncacheable data. And it was very general purpose. And I'd be curious to hear your comment on that.
So I guess the concept of uncacheable writes to memory isn't novel. Just like logging for implementing persistent memory isn't novel. A lot has been done before, but I'd say that right now RISC-V doesn't support that functionality, and I think that, or at least not to the extent that I've seen. Sorry? Yeah, it's not complicated, but I still think it's a feature that's important to have.
So a couple of points. I'm up here.
Oh, yes, hi.
Hi. There are a couple, well, actually you're right, it isn't supported directly in the page table. However, there are 2 reserved bits in the page table which conceivably could be used for that. The question I have is whether you expect that the same address will be cached or uncached depending on which op you use. Because if you say that this area of memory is going to be uncached and that part of memory is going to be cached, then there's already the capability of doing that in the current architecture with the physical memory attribute table.
Yes, that's true. And in fact, some persistent memory works do rely on the fact that the log can only exist in a certain address space of memory, separate from where your working data is. But other works don't rely on that fact. So ideally, we would like to be able to specify, this write due into this address, even though it's not in some reserved cache or uncached part of memory, but we can say, hey, this write will not be cached. So that's a good point, and it's definitely something that I've considered before, yes.
You proposed instruction to invalidate the cache line. Assume you are not alone in your memory system and somebody else changes the memory content behind the scenes and you don't want to afford a coherency manager.
Yes, that's a good point. So there's multiple ways to flush the cache. Older cache flushing instructions do invalidate the cache line, and it's important to be able to do that. But I suppose that in fact, this is a proposal, and I do think that having an option to flush and invalidate would be just as useful as flushing and not invalidating. So yes, that's a good point.
Thank you.